and trying to show the kind of the, non-Thursday, the links between Newton's laws and how Newton's laws will translate for things that are rolling or turning. So let's start with two different things. We're going to do, and I know it's like, it's just a Tuesday after a long weekend, but I don't care. You guys should be capable. Your homework's going to have problems like this. So let's take a look at what a typical kind of homework question could look like. And you've done this problem before. So this is why I expect that you would be good at this problem again. All right, so I think everybody can see this just fine. Gets the idea of what we have here. There we go. So let's say that this thing on the table is, we'll go with 6 kilograms. And the thing that's hanging is 2 kilograms. And we'll say that there is, we'll say there is no friction, and we'll say that this is 4 kilograms and has a radius of 20 centimeters. All right. I'd like to find the acceleration of this system. Now, based on what I think you can do, I think you guys could draw the free body diagram for each of the objects here. And I would expect you could draw or write out the net force equation for the block on the table and the block that is hanging. And if you paid attention Thursday, you should be able to do a net torque equation for the pulley. Let's just see if we can get that far, okay? So free body diagrams all around, net force equations for the blocks, and a net torque equation for the pulley. Don't look too concerned. It's in your notes from last time. Okay. It's very similar to the one you just did. So give it a try. First, I think, although we probably should start with the pulley, let's start with the block on the table, the easiest one. Although almost all of you universally drew an up and down arrow. Do we care about the up and down arrow right now? Bless you. God. You should be. Are you all done now?
Yeah.
Do you need a Kleenex? They sounded juicy.
No, I'm wearing juicy.
All right.
That was a wild response. That was just.
He was asking if I needed a tissue.
I asked if you needed a tissue.
Just calling a sneeze juicy and it's like in itself.
We'll just go on. We would only need the up and down arrows if we were concerned about friction. Because it's under those circumstances that we would probably need to figure out the normal force. We don't need the up and down arrows this time. They're not really contributing to the problem. If you drew them, great, because that's what you're supposed to do. But yeah, up and down arrows for normal force and weight. But this is a tension, right? And that's what's going to cause it to move. In fact, going one step further, net force equals 6A. I probably would have said tension equals 6A. Right, that's where you're supposed to go next. Now, let's consider the box that's falling. Here, a lot of you screwed this up, and you got to stop doing this. There's an upward force, sure, tension, but the downward force had better be greater than tension. If it's going to move downwards, the unbalanced force has to be in the direction you think the system's going to go. Many of yours, the box isn't moving, right? It's not moving because you made the arrows the same. A few of you, you made the tension arrow bigger than the downward arrow, so it's going to go up. That's a problem. Simple stuff, but we have to be better at it. This is 20 newtons. And if I were to write a net force equation, I would want this to be the positive direction for everything. So I would say 20 minus tension equals 2A. This next part is where you guys are all in trouble, and here's why we have to be more careful. And this is where the crux of today's conversation comes from. A free body diagram doesn't work for an object that is twisting or turning, because an object that's twisting or turning, the point of application of the force matters, meaning where the force is actually acting on the object matters. So you have to draw the object from now on if the object's going to twist or turn. So there are some forces many of you did write in, good job. You got things like the weight, and you put a weight downwards. That's got to be true. There's got to be weight downwards. Also, there's a tension downwards, but I'm drawing it at the outside edge, and a tension this way. Again, drawing it at the outside edge. Now, just these by themselves, this system would be unbalanced, and the pulley would go someplace. So there must be something that keeps the pulley from basically traveling this way, right? That's where the arrows are. So you should have drawn something like in this direction. Something's holding the pulley in place, but it's acting at the center. It doesn't cause a torque. These are probably the forces acting on the pulley. But there's something else, and all of you need to start thinking of it this way. This tension and this tension can't be the same. If they're the same, then the torque on the pulley is 0, and it doesn't twist or turn. Which tension is greater, the one going down or the one going to the left? The one going down has to be greater than the one going to the left if the pulley is going to turn this way. You have to draw it like that. So from now on, the tensions aren't the same. You need to make the tension in one direction different than the tension in the other to accommodate that the pulley has to spin. And this is the unbalanced torque. That means labeling it too. I'm going to make this T2 and this T6 to correspond to the masses. The two tensions are not equal. T6 does not equal T2. Before, our tensions were the same all the time. They're no longer the same. Some of that force is being used to cause the pulley to turn. So you need to label that correctly too. And make sure your diagrams are all in agreement. So T2 and T6. And label and label. All right, so first thing, adding to your notes, is that from now on, tensions aren't the same for these problems. Tensions are different. Next, there are forces that act on a pulley that don't cause torques. That's fine. So net force on the pulley is 0. But the net torque on the pulley is not 0. The net torque on the pulley is I alpha. Now, torque equations are a little more complicated. Remember, they have to have not only the individual torques, but they also have to have I. So you have to assess what the object is, use the proper moment of inertia, and you have to write the torques out correctly. So looking at this picture, can we recognize that the torque is applied at the edge? So our torque arm will be based on a radius of R. And as I said to you on Thursday, because this is a pulley, the strings always come off tangent, so they're always going to be a right angle. So although there are 1, 2, 3, 4 forces, there are only 2 torques. So remember, a torque is R times F times the sine of the angle. We're making this the positive direction. So there's the torque from T2, and then there's the torque from T6. Those are the only torques there are. I won't normally write them out like this. I'm doing it just this time because it's our first time doing one that has two different tensions and therefore two different torques. But T2 causes a torque that we'd write out as R times T2 times sine of 90 degrees. And then T6 is in the opposite direction, so I'm going to put minus R times T6 times the sine of 90 degrees. And adding these together is our net torque. So it's not really that hard. It's RT2 minus RT6. The sines of 90 go away. That's our net torque. So let's bring it all kind of together here. I'll have RT2 minus RT6 equals, all right, got more work to do. Pulleys are what? Are they a hoop, a sphere, a disc? What makes the most sense? Disc. You'll be told the shape in most cases. So let's just go with a disc. That's 1/2 m r squared. I know I put the mass in of m, and I could put the r in, but I want you to see something. This is times alpha. So we have written out our force equation for each object. We've written out the torque equation for the object that's rotating. But if we look carefully from what we've done, T is an unknown. T over here is an unknown. A is an unknown. That's three unknowns right there between those two equations. And although we have T2 and T6 here, we have a fourth unknown, alpha. That's four unknowns and three equations. That's not going to be enough. So it's at this point in the solution of the problem. We've done all the same steps. I don't know if you guys have put this together, but these are the same 4 steps you had first semester, right? Determine if it's a first or a second law problem. Draw a free body diagram for every object that has mass. The only thing different is that you have to stop. And when you have an object that's going to be experiencing an unbalanced torque, you have to evaluate the torques. That's a new set of steps, right? A new set of things that you have to be able to do. So if we're looking at the things that we have to add, this is one of the things you have to add. It wasn't in our original discussion for forces, but we have to add it for torques. The other thing, we often talked first semester about choosing a direction to call positive. We've done that, right? And we're saying that this is the positive direction for this box, and this is the positive direction for this box. We're also saying now that this is the positive direction of rotation for the pulley. Right? It's one more step of the things we have to do. Well, I'm adding another step. You have to decide if there's a relationship between the accelerations. You have to add this step, and you need to be conscious of this, because I can easily manipulate that one. And that's when it's easy for us to kind of jack with. So ask yourself if the motion of the boxes is connected to the motion of the pulley. Meaning, does the outside edge of the string move along the same as it does for the pulley and the boxes? If it does, then you can say that A equals alpha times R. This is exceptionally important. Take a minute to think about this before you proceed with your problem, and identify whether you can use it or not. If you can, it eliminates all the R's in this relationship. If you can, it makes the R not important. So let's see that it gets done. Let's watch. We're going to say RT2 minus RT6 equals 1/2 times 4 times R squared times A over R. your algebra skills sometimes need some help, so let's take a look at doing some algebra. Do you notice that on this side, one of the r's cancels? So let's write that step out, 1/2 times 4 times r times a. This side, do you notice there's an r in every term? So factor the r out. And do you see that we have an r on this side and an r on this side? So we can divide it across both sides and then write this as t2 minus t6 equals 1/2 times 4a. Doing this one simple substitution right here simplifies the problem a lot. It puts everything in terms of a. I would highly encourage you to put everything in terms of the linear acceleration. Do that, it makes the problem easier to solve. Even if they ask for an angular value, put everything in terms of the linear acceleration first, and then go back and convert it to angular if you have to. But start there. Now, you have two other relationships. They're not on the screen, but do you remember what they are? They should be in your notes. Because we've got T6 equals 6a, and we have 20 minus T2 equals 2a.
T equals 1/2 and r.
Where do you have that? Like from this problem or last week's problem?
From last week.
Yeah, that would be this one. That's what you got from the one from last week. But I think this week we have just these three because we have this force equation, and this torque equation. I just wrote them all together here. You see what I've done?
Yeah.
Okay. So this is the torque equation. This is the box on the table. This is the hanging box. Just like last semester, you get one equation for each object in your problem. It's the same thing. And if you do it right, you should be able to eliminate all the tensions. Do you notice that T2 and T2 cancel out? If you add those together, those two are going to cancel out. And do you also notice that T6 and T6 cancel out? Do you guys see that okay? So if I add it all together, all I get is 20 on the left, the weight that's being hung. On the right, I have 1/2 times 4a plus 6a plus 2a. (20) is the unbalanced force. 1/2 times 4 plus 6 plus 2 times a. This is the pulley. This is the block. And this is the hanging block. Do you see what this looks like? I mean, I'm trying to throw it in your face. I'm hoping you're putting it in your notes. Unbalanced force. Inertia of system. Acceleration of system, right? You get Newton's second law again. The only difference between first semester and second semester is we have this port, the pulley. It shows up. Its inertia is in the problem. Let's get all that out of the way. Now this is just math. I can trust you to do math, right? 1/2 of 4 is 2, 2 plus 2 is 4, 4 and 6 is 10, so this whole thing is A equals 2 meters per second squared. If you want one of the tensions, you can go back and get one of the tensions. If you're asked for the angular acceleration of the pulley, you can get the angular acceleration of the pulley. Right? It hinges on getting the acceleration of the system. Well, we're going to see if you guys got that or not. You're going to do the one other example. I'm not going to change very much here. Same pulley. So 4 kilograms, 20 centimeters. And I'm going to take the box that we had a moment ago and the other box that was on the table. So 2 kilograms and 6 kilograms. And I'm going to hang them like this. Your job is to find the acceleration of the system. Same problem, very similar. I'll give you 5 minutes. Work with the group. Come up with A equals. I saw some problems. So the answer is 4 meters per second squared. Did you make this way positive? Good call. That way should be positive. Right? Because this one's probably going to go up, that one's probably going to go down, and this system's probably going to rotate that way. Yeah? Then you would get -4 if you made the other way positive. Yeah? Before you walk out, if you've done it right, you'll get something that looks like this. 60 minus 20 equals 1/2 times 4 plus 6 plus 2 times A. I know we don't meet as a class, or if we do, it's like 2 minutes, but good luck on your SAT